Welcome to the APL quest. See APL Wiki for details. Today's quest is the fifth from the 2016 round of the APL problem solving competition. We are to find the elements of a list that are only once in that list, that is, those that have no duplicates. Let's start by defining a function. It's an anonymous function. We're not giving it a name right now, but we're going to apply it to an argument. A very simple way to go about this is to compare every element in this array, let's say list, a vector, a one-dimensional array, to every element. That is, we're making a comparison table. So we take the argument and compare to the argument, but we want to do all combinations, so not just equality, but this jut dot together makes a table. So this is a equality table. And so imagine that we have the letters of hello world going down on the left and going across on the right. And we can see which elements match which elements. And of course, the diagonal is all ones because elements match themselves. But we can see that there are duplicates when they match multiple. And so, by counting how many matches there are for each element, then we can see which ones only appear once. And we can do so by summing. So if we sum along the columns or along the rows, it doesn't really matter, but let's just do the columns for now, then we can get a count per element. And sum is a reduction using plus. So we use plus, and this slash bar means reduction. And you can see here that each number corresponds to how many ones there are in the column above. Now we want only the numbers that are 1, so we can compare 1 to all of that. And we can see here that the ones compare, we get a 1 a true where we have a 1. And then we just need to filter the argument using this bit mask. So we take this bit mask and use it to filter. We can do that again with a slash bar, but this time we have a mask on the left, so now it doesn't mean reduce, now it means filtering, also known as compress, on the argument itself. And we get H and E that only appear once. The L's, there are 2 of those. There are 2 O's, so we skip that. There's a single space. W appears once, and so on. So this is one solution, albeit and not very good one, because it does a lot of computation that is unnecessary. For example, this table is way bigger than it needs to be. We don't need to compare every element to every element. We could compare just to the unique elements. So how can we find the unique elements? Well, we can use the unique function, which looks like a U. And this gives us just the unique elements. Now we can compare to those. And this gives us a smaller table. And if we now count how many there are of each of the unique, we get a mask we can then apply to the unique. And we get the same result with a little bit less computation. Wait, we are computing the unique twice. That seems a bit wasteful as well. So we give the computed unique value a name, U, and then we can use that over here, which is a bit better. That said, APL can actually do a lot of this for you, and it will do so more efficiently by using the built-in that's made exactly for this kind of work. So let's remove everything here. We have the argument, and there's a special operator, it's called, which is a higher order function called key. And it takes a function on the left and applies this function to some properties of the argument on the right. It's applying this function over and over again, once for each unique element. So there we have it inside the unique elements. And the unique elements are given as left argument whenever we apply. So alpha is the left argument, being the leftmost character in the Greek alphabet. And as right argument, omega being the rightmost character in the Greek alphabet, it gives all the indices where this unique element occurs. So we can see that the H appears only in position 1, E only in position 2, L appears at 3, 4, and also at 10 over here, and O at 5 and 8. Now we're not actually interested in where they are, we're only interested in how many there are. So we can get rid of the left argument, and it gives us just the indices. And we're not even interested in what exactly the indices are, but just how many. So we use tally, which looks like a tally mark or like a counting stick. And this gives us the counts for each one. So this was the same we got before when we made the table and summed the columns. And then we can take it from here. We can compare to 1 and use this as a mask on the unique elements. And this solves the problem. But this key operator actually computes the unique elements by itself, and we're also computing the unique elements outside, which isn't the best. But remember, we can get the unique elements as left argument in this function, which means the information is actually available. We just need to change the structure of the result coming back so that we can get all the information we need and apply it. So let's try that. We have the count over here, and we can actually do the comparison with 1 in here as well. Then we get this mask directly. And then we can concatenate the left argument, which is the unique element. So comma is concatenate. And we can say we get this table of which ones are the ones that we want, which means we really have a mask here, and we have the data over here. We just need to apply this mask, this column, to the column on the left. As we saw before, the filtering function, also known as compress, takes the mask on the left and the data on the right. So we really want to have the unique elements on the right and this mask generating expression on the left. We could put parentheses around this expression and move the comma over on the side, but we can also use a special higher order function or operator called commute, which takes this function on the left, much like key takes this user-defined function on the left, and the only thing it does to it is it changes the order of the arguments. So the left argument becomes the right argument, the right argument becomes the left argument. And this just gives us the two columns in opposite order. And now we want to break this two-column table or matrix into two vectors. And we can do that by concatenating vertically. So we're concatenating the first element over here with the first element over here, and so on. And concatenating the second element with the second element. So we want to concatenate vertically. So just like we used the slash bar as a vertical sum, now we're using it for vertical concatenation. And that gives us these two elements, which are the mask and the data that we want to apply the mask to. Before, we used compress infix. We used it between two arguments. But now we have the two arguments in a list next to each other. So we need to insert the compression function in between the elements, which is again a type of reduction, but just over two elements. So slash bar here means the filtering or compress, and then slash bar again, because it has a function next to it, it means insert or reduce. Now there's one little issue here. You can see this box around the result, and that is because we start off with a vector, a list of 2 elements, which has a single dimension. We're counting 1 element and then 2 elements. And reduce, the name implies that it needs to reduce the rank, or the number of dimensions. So it goes from 1 dimension to 0 dimensions. How can it have a multi-element array in 0 dimensions? So it packages it up in an enclosure. That's this box we're seeing. But we can disclose that. We open it up. So this kind of looks like a mouth that is away from the array, and it opens it up. And that gives us our result. So this is another solution. And finally, a really clever solution that somebody came up with. There is a function called unique mask, which instead of returning the unique elements, it returns a mask indicating the first occurrence of every unique element. That's this equal sign with only one, an unequal sign with only one argument on the right. So this says that h is the first, and the first h is the first is h, and this e is the first e, and this l is the first l. This l is not the first of its type. Now, what we're actually interested in here is to remove all the elements that are duplicates. So which elements are the ones that have duplicates? Well, that would be the opposite of the ones that are the first. So if we use logical negation here, then yes, we need to remove all the L's, and this, if we use this mask, it would not give us an L, but this would give us an L. So we're guaranteed for every element that has, every unique element that has duplicates, we're guaranteed to get at least one element from this mask. And so we can apply this to the argument itself. So we're using this compress function, but the mask needs to be on the left, so we commute the arguments. And this gives us all the elements that we want to, all the types of elements, unique elements that we want to remove. It doesn't matter that there are duplicates. Now we can take the argument itself, and then we use set difference. So if you use the tilde with both the left and the right argument, it doesn't mean not, the Boolean not. It means but not, or except. So it's set difference. It's everything here on the left, but not those things that are on the right. And that gives us the elements that appear only once. Thank you for watching.